All right, good morning. Thanks to everybody that could join us this morning and taking some time out for this. I am Grant Neas with Rhythm Engineering. Just to kind of give you a little overview of what I do here at Rhythm. I'm the senior project engineer and am responsible for all the configurations that are deployed out in the field. So the adaptive setup and the adaptive calibration of the systems that are deployed falls under our project engineers here at Rhythm. So kind of the goal this morning for this this webinar and this presentation is to give you a real high-level overview of how the InSync algorithm works. You know, the decisions it makes and why it makes those decisions. So that's what we'll be going over, and we'll get started then. So the two primary topics we're going to be covering this morning are the global optimizer and the local optimizer. Now those two optimizers are two independent algorithms within the InSync system, but they do have some relationships to each other, and we'll go into that here shortly. So when I talk about the InSync algorithm, I like to explain it with three different components of the model. And the first component is what we call the period length. And that's really the constraint of the system. And why it's the constraint is there's a few rules that have to be satisfied over the course of a period length. And we'll get into what those rules are. But that's kind of the constraint of the InSync system. And then the two other components are what we call the global optimizer, or otherwise known as our tunnel time. And then the last component is the local optimizer, and that would be our non-tunnel time. So any time outside of your tunnels is what we would call our local optimization time. You can see on the screen currently that I have a snapshot or a cutout of a time-space diagram. So what you're seeing up there is that on the horizontal axis you have distance, and on your vertical axis you have your time. So the orange tunnel you see right there is a tunnel that's crossing, you know, two intersections. Each vertical black line there would be representing an intersection at a certain, you know, space along your corridor. So to jump into the global optimizer, the primary goal of the global optimizer is to facilitate progression between your intersections on the InSync corridor. So that's really what the global optimizer is trying to do, and it's really its main function is. So the first major parameter and term that's used with the global optimizer is what we call a tunnel. So a tunnel is basically the coordinated movement at an intersection. And more importantly, it can be any phase. So it can be a side street phase, it can be a left turn phase, and they can be different phases at each intersection. So if you want to coordinate off a left turn phase at one intersection and, you know, coordinate a through phase at the downstream intersection, you can certainly do that. You just define which phases are your tunnel phases. So a big question I always get is, okay, so what's the difference between a tunnel and a traditional green band? Well, the biggest difference is that a tunnel can shrink or extend based on local conditions at each intersection. So it may shrink at one intersection, and then at the next intersection it may extend. And it's making those decisions every single period through. So it has that flexibility to increase or decrease that green time of the coordinated movement based on the amount of traffic that's actually at your intersection, and more importantly, the amount of traffic that's coming through on your coordinated tunnel phase. So with this illustration down here, what you're seeing is again a time-space diagram, and the tunnel length is illustrated there by the orange band and the green band going each direction. The tunnel is a user-defined parameter, so it is a duration that goes into the InSync system, but I like to explain it a lot of times as a baseline duration computed on expected conditions, because if those conditions do change, it has the adaptability to increase or decrease based on what it's seeing. Okay, alright, so now let's talk about the period length. So the easy definition of what the period length is the time between successive tunnels. So really the time between one tunnel starts and when that same tunnel starts again later in time. So as you can see on this diagram, the time is between when that orange tunnel starts and when it starts again in the future. So that is what is considered the period length within InSync. Okay, so back to the period length. Two rules that define the period length and have to happen every time through are: you have to serve all your coordinated tunnels. So whatever you have defined as your coordinated tunnels have to be serviced every period length. And then the second rule is you have to serve all occupied phases at least once per period. So the key word there is, at least once per period. So InSync has the flexibility to reservice phases if there is extra time after all phases have been, all occupied phases have been served once. There's extra time before the next coordinated movement comes through. InSync has the flexibility to reservice phases based on the demand that it's seeing. So, like the tunnel length, comparing to the traditional green bands, I get a lot of questions. Okay, what's the difference between a period length and a traditional cycle length? Well, the biggest difference is you don't have as many restrictions. With a cycle length, you have inherent maximum green times that you have to input into the plan that you have set up. Also, you have to input a ring and barrier structure that defines the sequence of phases that are serviced at an intersection. Well, a period length, what it does is it simplifies it down a lot and removes a lot of those restrictions that are inherent to a cycle length, including the ring and barrier structure and including the maximum green times. So you're really only looking at these two simple rules that have to be satisfied every period length. And that's really where the biggest difference between a period length and a cycle length is. Okay, so far we've talked about what a static period length is and how that is adaptive relative to a traditional cycle length. Well, one thing I haven't talked about so far is what we consider our dynamic period length. So the dynamic period length allows InSync to increase or decrease the period based on real-time conditions at all the intersections on the corridor. So the basic way that the algorithm works for the dynamic period length is really a simple statement, and it's basically, did the intersection clear out all its phases or did it not? So if one intersection reports and says, hey, you know what, I went green and then I went amber into red and I still had a standing queue there, it's going to report back to what's considered a facilitator intersection, which handles the dynamic period length adjustments. It's going to report back and say, you know what, I didn't have enough time to service all my phases. I would like to increase the period length. The facilitator intersection then makes the decision of, okay, how much do I need to increase the period length by? Likewise, if every intersection reports that it had cleared out all its phases and had extra time, then the facilitator will lower its period length. So with that being said, it's a little bit easier and quicker for Insync to raise its period length because only one intersection needs to request a bump up in period length, whereas every intersection has to agree in order to lower its period length. And that's really how the dynamic period length algorithm works behind the scenes. So one thing to keep in mind with Insync is that there's not a traditional offset that is inputted into the Insync system. The offsets are actually calculated from what the current period length is and what the travel time between intersections are. So with that information, Insync can automatically compute what the offset should be. So you don't need to manually adjust offsets as the period length increases or decreases. It automatically does that, and that's how it gets away, or that's how it doesn't have to go through transition when it changes its period lengths, because it knows how to automatically adjust the offsets between intersections. Okay, so to just illustrate what's happening when the period length is changing, you'll see here on the left side of the screen again a cutout of a time-space diagram, and you'll see that to the left of that diagram you've got 100 seconds there. That's what the current period length is. So if Insync increases the period length, what it's doing is it's actually increasing the time between the orange tunnel that's coming through. So what it's doing is it's increasing the white space between those two intersections, which allows Insync to allocate that extra time to any movement at a phase. It doesn't have to allocate it to a side street. It doesn't have to allocate it to the main line or a left turn. It has the flexibility to determine which phase that it should be allocated to based on real-time conditions, as it's making these decisions second by second. Okay, so just to kind of recap, the global optimizer, again, the goal of it is to facilitate your progression between intersections. And then there's two major components of the global optimizer, being your tunnel length and your period length. And we went over exactly what those mean and how they relate to maybe some of the traditional things that have been done in the traffic industry. So to move on to the next algorithm behind Insync, which is the local optimizer, the major goal of this is to reduce the delay of your non-coordinated phases. So it's really trying to, outside of the tunnel time, it's trying to intelligently determine how can I reduce the delay of each phase that hasn't been serviced yet. So we'll go into that a little bit more. So the first major component of the local optimizer is this statement you see here on the screen right now. And what it is it's a statement on how Insync determines whether to force off a phase. So in other words, it's how Insync computes its maximum green time, if you will. But the key here is it's not computed before the phase is serviced, or the previous period, or 5 minutes ago or 10 minutes ago. It's actually computing this every single second as the phase is currently green. So what it's looking at is it's saying, okay, once my time until the next tunnel is less than or equal to the time to serve your remaining phases that haven't been serviced yet, once that statement is satisfied, it will terminate the current phase it's on. And that's how it determines how to force off phases. So to elaborate a little bit on each one of those items, I'm going to go into a little bit more into depth into each of those. So when we're talking about how InSync computes the time until the next tunnel, it's pretty simple how it does that. But to illustrate it here, again, we've got a snapshot of just a time-space diagram. In this case, we're just looking at one intersection. So that one intersection would be the blue vertical line you're seeing in the middle of that diagram. On the bottom, you see the two hash marks there. Those would be denoting the tunnels that are coming through that one intersection. And again, that would be the global optimization time or the tunnel time of an intersection. So as soon as that tunnel time or global optimization time ends, it transitions into what we call our local optimization time. And that's immediately when it starts computing, okay, how much time do I have until the next tunnel comes through? So as time goes on, obviously that value, or that time value, will go down. So every second, it'll shrink by a second until you actually meet, you know, the time, or the next tunnel. So it keeps getting smaller and smaller as time goes on. So that was, you know, how time until the next tunnel and how InSync computes that. Now let's jump into, okay, how does InSync actually compute how much time to serve the remaining phases that haven't been serviced yet? Well, what it does is it counts up the number of vehicles, and the way it can count those number of vehicles is with the InSync cameras, and those cameras can report a queue every single second. So every single second, InSync is reading the queue at all approaches. So it counts up all the vehicles, and it multiplies each vehicle times 2.1 seconds. So InSync internally gives a value, a time value of 2.1 seconds in order to clear each vehicle. So that's how it's computing the amount of time. So it multiplies the number of vehicles times that 2.1 second value, adds in your clearance intervals, so your amber time and your red time, and that gives you your time to serve your remaining phases. So let me illustrate that with a couple examples here. So this first example, let's say you have a standard 8-phase intersection with 8 phases, okay? Or I'm sorry, with protected left phases, rather. So, and you'll see up here that I've got example queues. So for your westbound left, there's 7 vehicles. For the westbound through, you've got 4 vehicles. For your eastbound through, you got 8, and eastbound left, you've got 6 vehicles. So what InSync does is it takes the greatest of the conflicting phase pairs and compares those. So, for example, what it's going to do here is it's going to look at your conflicting eastbound or eastbound left and westbound through and sums those up and says 10 vehicles. And it compares that to your other conflicting phases, which would be your westbound left and eastbound through, which gives you 15 vehicles. You know, 8 plus 7 giving you your 15 vehicles. And it's saying, okay, that's greater than the 10 vehicles, so that's the amount of vehicles I'm going to allocate time for. So what it does then is multiplies the 15 vehicles times that internal 2.1 seconds per vehicle value, which gives you, a value in this case of 31.5 seconds. The next step is for it to take into account the clearance intervals, and in this particular example, it's going to be taken into account 3 clearance intervals. And I get the question a lot is, okay, well, why are you taking 3 clearance intervals? Shouldn't it be 2 if we're just talking about, side street phases? Well, the reason it's 3 is because this computation is happening while a phase is currently green. So it has to take into account the clearance time to shut off the current phase, the clearance time to shut off, between the 2 side street phase pairs, and then also the clearance time to go from the side street back to the main line for the start of the tunnel. So that's where those 3 clearance intervals come into play. And in this case, I just used, example values for your all red and amber. Those values would be based on what are set in the controller at your intersection. But you take all those values together, you add them up, and you get a total time. In this case, just about 50 seconds. So let me give another example of a little bit different geometrics at an intersection. In this case, a split phase intersection. So instead of taking, the conflicting phase pairs and summing them up and taking the greatest, the math is a little bit different because you can't serve, your two different side streets at the same time. So InSync knows how to take that math into account to compute how much time needs to be serviced for the remaining phases. So in this case, what it's doing is it's taking the greatest of each side street split phase. So in this case, it's taking 10 vehicles on your eastbound split phase, adding that to your 7 vehicles, which is the greatest of the lanes over on your westbound, and it adds those up to give you 17 vehicles. So just like in the last example, it's going to multiply that by 2.1 seconds, take into account your clearance intervals, and it's going to give you a total value of, in this case, 54 seconds. The biggest thing to take away from what I've just explained and illustrated is that this time to serve remaining phases is computed every single second. So in this case, if another vehicle shows up on one of these phases, a second from now, then it'll increase that time to serve remaining phases by 2.1 seconds. So it's constantly reevaluating this statement and how to compute the time to serve your remaining phases. Okay, so sometimes I like to explain this as what's considered a dynamic max green, or our version of the max green. But the key there is that it's computed every single second, and it can change from second to second. So it's not something that's computed before phases turn green. It's actually computed while phases are actually green. So we think that gives the most efficient operation as far as how to force off a phase. Alright, so let's move on to a couple scenarios here. Illustrating that statement we just talked about. So this first scenario, let's say there's just one car on your side street, and InSync knows there's only one car because it's getting a Q value from its cameras. And traffic is continuing to flow through on the main line even after the tunnel duration has elapsed. There's still traffic coming through, whether there was mid-block generator or the platoon was just longer than it typically is. What InSync's going to do is it's going to say, okay, well, there's only one car on the side street. It'll only take me minimum green in order to service that one vehicle. So what InSync's going to do is it's going to say, let's keep extending the main line, even though it's past what I guess traditionally would have been considered its computed max green time, because it knows there's only one car on the side street. Saying, I'm going to make that one car wait just a little bit longer so I can get these at-speed vehicles through the corridor. And so what it's doing is it's giving a preference to those at-speed vehicles on your main line to get them through the corridor. And you're reducing your overall delay by doing that. Because what traditionally would have happened in this scenario without InSync is the main line would have hit whatever pre-computed max green time that was set up in the plan. It would have hit that value, it would have went over to the one car on the side street, and then it would have gapped out that one car and returned early to green. But what you're doing there is you're making that whole tail end of your platoon, however many vehicles it is, stop and then start up early, and then they would just have to stop at your next intersection. The idea behind InSync is it's trying to always get that tail end of your platoon through as long as it can by weighing how many cars are on your side street. So let's look at a second scenario. Let's say it's the opposite scenario where you have a ton of traffic on your side street, in this case 50 cars. And you have the same scenario where you have traffic continuing to flow on your main line even after your tunnel has ended. What InSync is going to do is it's going to terminate the main line immediately after the tunnel has ended. Because it knows those 50 cars, the amount of time it's going to serve those, it will take to serve those 50 cars is greater than the amount of time it is to the next tunnel. So it has to terminate the main line right away after the tunnel is ended. So in this case, that's very similar to what a traditional system would do. It would hit its max screen time, go over to its side street, hit its max screen time, and come back to the main line. The main difference you see in the efficiency of InSync is when you have that extra time, and InSync is able to make intelligent decisions on what to do with that extra time. Okay, alright, so just to recap a little bit, we've talked about global optimization with period length, tunnel lengths, and then we've talked about how InSync forces off phases, how it determines to terminate a phase. Well, now what I want to go into is how InSync determines the phase order or the sequence at an intersection. The key thing here is that InSync takes into account geometric and safety restrictions first. So that's all inputted into the InSync configuration as far as what phases can run with each other and what order of phasing is allowable. So if you have protected permitted lefts that create a yellow trap, InSync will know not to attempt to lag a left turn. Or if you have split phasing operation, it'll know to not bring up your two side street through phases together. It takes that sort of information into account first. And then it looks at, okay, the pool or the sequences left that it can pick from in order to service phases at an intersection. And the way it chooses from those pool of sequences is it chooses the phases with largest demand and chooses a sequence where they're serviced first. So when we talk about demand, it's a combination of wait time and queue length. And it's a near product of wait time and queue. It's not an exact product, but it's pretty close of those two multiplied together. Okay, so let me give an example of a location where I've actually grabbed a snapshot of what InSync's decision making is happening at a specific instance. So in this case, I've grabbed the snapshot immediately after the mainline tunnel has ended, and the mainline tunnel was on northbound and southbound. So your two left camera views here were what would be considered your tunnel phases. So I grabbed it the instance that it's shutting that down and moving over to the side street. So what you'll see InSync look at is it's looking at the wait times for all your side street phases as well as the queue lengths. So in this case, the eastbound left and eastbound through phase is has a higher wait time, and it has a higher or larger queue length for both its phases than westbound or westbound left. So what InSync's going to choose in this case is to lead the eastbound left and lag the westbound left, because the eastbound demand was higher than the westbound demand. Now if this changes the next period through, let's say it's the opposite, where westbound has the higher demand, a higher queue or higher wait time, then InSync may choose to lead the westbound lefts and lag the eastbound lefts. So that can change every single period, and that's really how you're reducing a lot of that local delay that you would have previously with a fixed sequence. Okay, alright, so let's talk about how InSync gaps out. So InSync will utilize a percentage of occupied detection zones in order to gap out its phasing. And the default value that InSync uses for that is 25%. So anytime a percentage occupancy of a phase drops below 25%, InSync will immediately gap out that phase. So what it does is it allows, the last car to clear through on your amber time, basically, and you won't have that wasted green time that you would otherwise have with a traditional extension timer or passage timer. There is the capability to use a traditional extension timer or gap timer in InSync if that's something that you want to do. So that capability is there, but we do recommend using the percent occupancy because it is more efficient. So let me illustrate that a little bit more on how you're actually saving time. So what you see here is on the left side you've got an installation or an approach with InSync, and on the right side you have an approach without InSync. So on the left side with InSync, you've got InSync's cameras that are computing the queue. How many cars are there? And then on the right side you have a, let's just say a traditional loop in the first segment down there for detection. So, at time equals 0, you see InSync is reporting a 40% occupancy, which is larger than 25%, so it says, okay, let's go ahead and extend this phase. Without InSync, the loop is triggered, so it says, okay, extend my phase. Say we move a second in the future to t equals 1, and you'll see that InSync is reporting a 30% occupancy. Again, greater than 25%, so it reports, let's extend that phase. Without InSync, the loop is still triggered, so it says, okay, let's extend. So now you'll see once it hit t equals 2 that with InSync it actually dropped below 25% to 20%. So InSync is going to gap out immediately once it drops below 25%. So it's gapped out at t equals 2. And you'll see without InSync that there's still a car on the loop, so it's saying, okay, I need to extend. So let's move a second into the future, and you'll see that again, without InSync, there's still a loop trigger. And then finally, you'll see at t equals 4, the passage timer starts. So, at t equals 4, the passage timer is elapsed for 1 second. At t equals 5, it's elapsed for 2 seconds. And then finally, at t equals 6, in this example, I just used a 3-second passage time. You'll see it gapped out at t equals 6. Well, you'll see a huge difference there between when InSync gapped out at t equals 2 and when without InSync gapped out at t equals 6. You save 4 seconds of what is considered a completely wasted green time at the intersection. So that's very powerful for InSync to be able to gap out phases that way, because you really can save a lot of wasted green time by using that mechanism to gap out your phases. Okay, so that was all going over today. Again, thank you for your time. If you do have any questions of anything I went over, you can write those down. Right now, it doesn't look like we do have any questions, so I certainly appreciate your time, and if you do have any questions or think of any, you can always reach out to me. My email address is grant@rhythmtraffic.com. So, thank you. Bye. Done?
Cool.